method to determine in situ stresses, like in situ reservoir characterization. If you want to determine in situ stresses, we do some like a small scale hydraulic fracturing, and then close the fracturing and measure the fracture closure pressure, and based on that we determine the in situ, like so the problem is that if you get the rock core and you can try to do some analysis in the lab, but that is that like properties which you get from a lab, they are not very like representative from the field. So sometimes we need field scale testing. So their hydraulic fracturing uh, is extensively used. Another area which is like emerging area where hydraulic fracturing will have high potential, particularly in the CCUS, where we want to increase injectivity of the reservoir rocks by fracturing the reservoir rocks. So what basically we do in hydraulic fracturing? We do in hydraulic fracturing like we inject like huge kind of like million gallons of fluid, which can be like water and some chemical, some propane, the material and some chemical, and we inject that at high pressure. Let me see here. We inject that fluid at high pressure, and as we pressurize, it will create these fissures, cracks, and then first we inject the fluid and it will create this fracture, and then we mix with the sand like kind of propellant to keep this fracture open, and then once we finish this job, uh, cracks will give like conductive path for hydrocarbon recovery from. So that's the basic of hydraulic fracturing, what we do in hydraulic fracturing. So So let's say why we need hydraulic fracturing, essentially, particularly in oil and gas reservoir. So like I mentioned earlier, we need to increase the reservoir permeability, particularly in the low permeability reservoir like shale and tight oil and gas reservoir, like tight sand reservoir and shale reservoirs, so where we need enhanced reservoir permeability. And also we can by hydraulic fracturing we can increase the drainage radius from a well, and additional part where we need hydraulic fracturing to let as we drill near to drill like near the wellbore, some mud cake and damage happens due to drill cuttings, and they can basically block your conductive path for the hydrocarbon. So their hydraulic fracturing is also very useful. And by hydraulic fracturing we can also reduce stress concentration, and also we can control the sand production. And also like I mentioned earlier, for CCUS case, we use hydraulic fracturing to increase injectivity of a well for injection purpose. And overall hydraulic fracturing can increase the economic life of a well. So these are the main like factor why we need to do hydraulic fracturing in the oil and gas well. So let's see what the basic mechanism for the hydraulic fracturing. So basic mechanism hydraulic fracturing uh, is basically depends on the stress concentration and near the like on the wellbore. So it's basically it's like if you have this horizontal stress, maximum minimum horizontal stress and maximum horizontal stress, and also we have the top and the vertical stress. So using that we can calculate the stress concentration at the wellbore using stress solution. And in order to hydraulic fracture to initiate from the wellbore, your fluid pressure should be higher than your smallest principal stress plus tensile strength of the rock. And if we solve this solution at wellbore, this expression results like so wellbore your injection pressure or breakdown pressure, we say it should be at least it should be greater than 3 sh min minus sh max. And this part is coming for the thermal part. If you have the temperature difference between reservoir rock and your injection like fluid temperature, so some of this thermal stresses will also develop. It will also help in hydraulic fracture creation. So if we drop this thermal part, particularly for the oil and gas, this is more useful for geothermal reservoirs. So expression for for the breakdown pressure comes like this, which is basically function of your horizontal stresses and tensile stress. And one important thing is to look for the hydraulic fracture propagation path, because it's always follow the local SH max direction, which is the least resistance path for to hydraulic fractures to open. So this will start from in the SH max direction. Basically, it's always propagate perpendicular to SH min, where it gets the least resistance. So let this ones we can see this is basically pressure during hydraulic fracturing. So once we pressurize the wellbore, initially the wellbore will take the fluid, and the fluid will basically have some compressibility. It will get compressed, and the pressure will build up. At one point when it reaches to stress condition, like we say in your pressure is to the point where we are satisfying this condition or exceeding this condition. So at this point, your breakdown will occur. And once the breakdown occurs and the pressure start propagating, the fluid pressure start dropping again. And then it's kind of get stabilized. And at this point, if you like shut down your pumping, the pressure will start declining. And declining is almost will come to close to your assessment. It almost goes to zero. And and the second now, so this is the first cycle. And if you do the second cycle on that same well, if you do the second cycle of injection, right, since the rock is already broken at that point, so the tensile strength disappear from there. So now your breakdown pressure will be less than your earlier. So basically, this math, like pumping two cycles, we can also determine tensile strength of the rock, because at this point, let's say your breakdown pressure here is PB, and breakdown pressure per secondary secondary cycle is PSB. So your tensile strength will be basically PW. PB minus PSB. So this can be also used to determine tensile strength of the rock in the field. So let's look again the model. So model is very similar like we discussed yesterday. So it's still like indirect boundary element method for rock and solid fracture deformation modeling. And the fluid flow, I simulated using finite element method. And there is propant transport and deposition also. So once you fracture the hydraulic, you created the hydraulic fracture, you need to keep them open. So that's why trying to pump the propant. So you need to also have the propants in your model. So and then the fracture is basically fracture propagation is simulated using linear elastic fracture mechanics. And there is additionally, because the additional complexity in the hydraulic fracture, because your fracture geometry is changing with the time. So in the simulation, you have to always maintain your like your mesh. So simulation mesh, you always need to keep updating, because you have to optimize that thing, like fracture geometry also. And I will show when we have this some interaction between hydraulic and natural fractures. So there we need additional criterion to determine how when hydraulic fracture is going to intersect natural fracture, or when it is going to cross. So that's also included in the model. So let's say some about the coupled solution in that one. So with this model, basically we need three variable. No, basically it's four variable. Once like three modes of fracture opening, normal opening, and in plane shear and out of plane shear. So we need three type of displacement of fracture surfaces. And additionally, we need the fluid pressure. So these two quantities here, this the fracture deformation. This is like normal, not DD 33. That is basically the displacement discontinuities. So it's particularly for the spacing method. So DD3 gives you normal opening. So normal opening for fracture and the fluid pressure in the fracture, they are like fully coupled processes. So they need to be solved in a fully coupled manner. So here I do the fracture deformation using the boundary element method. Then we do the fluid pressure, and this, let's say So this my fracture model. This take the pressure as an input from your fluid model, and the fluid model takes fracture width from your fracture model. So they are kind of fully coupled, and they need to be solved iteratively. So and additionally, we have this propant concentration. So once we solve this pressure and pressure width solution, the pressure width and the pressure, they go to propant model, and then we simulate the propant. And once the one cycle completed, we again go back to this cycle where we solve the fluid pressure and fracture deformation, and then go to propant. That's why we as we propagate the fracture, these three steps have to be solved at each propagation step. So let's see how the fracture will behave in oil and gas reservoir. So like I said earlier, most of this oil and gas like unconventional reservoir in particular, earlier like conventional also. So they basically have the sedimentary rocks. So they have kind of bedding planes. So all time the pay zone is either fully contained with with hard, like we can higher stresses zone, or with the higher like some relatively low barrier zone. So this case we have a pay zone which is like contained with very high stress like 10 MPa stress high. This is pay zone, and this stresses here in upper zone and lower zone, they are like almost like 10 MPa higher than the pay zone. And now see how the hydraulic fracture will propagate in this case. So let's see how the fracture will behave in this case. So initially it will, as long as we are here in pay zone, it will go the. Sorry, I think I have to. IPI use the laser. So if once yes, replayed. So initially the fracture start as radial when we are here in the pay zone, and once it will hit the barriers, it will start becoming kind of rectangular. So now it is fully contained in the pay zone. It's not going up and it's not going down, and that's very like it's useful because we don't want to like fracture go to zone where we don't have hydrocarbon, or is maybe some water table is there. So we want to contain that fracture. This is very good. Like containment of the fracture where we have very high stress, we can fully contain that fracture here. Let's see another case in oil and gas where we have a relatively weak barrier. Like we have seen earlier case, we have that stress barrier of 10 MPa. But in this case, instead of 10 MPa, we have 1 MPa barrier top and bottom. And let's see how the fracture will go in this case, will propagate in this case. So let's see how the pressure will go. So in this case, initially when the pressure is in the page zone, it's still going in the same manner, is radial pressure. And once it hit the barriers, it will start. So we can see that it should start going a little bit up in the upper and lower zone also, which was not in the earlier case. Since we have a relatively less stress barrier, so some part of the fracture is also going to the barriers like upper and lower zone. So these are very common kind of bedding planes which exist in oil and gas reservoir, and these type of fractures are mainly like occurs in oil and gas, and particularly in unconventional reservoirs. So now if we have multiple fractures, there is strong stress shadow. So when we have multiple fracture, each fracture start like restricting other fractures. So they like a kind of interference, and this case the fracture propagation is controlled by many things, particularly the stress shadow and perforation, erosion. Many concept is start. So we can see in this case if you do the multiple fracture simultaneous one is stress simultaneously fracturing, we can see this outer fracture they are getting like more propagation as compared to inner one, because they get the resistance from this outer fracture. They kind of get compressed, which is like kind of is called as stress shadowing effect. So that's how it will happen if you have multiple fractures. So this case, another many factors impact the results in petroleum oil and gas reservoir. Basically, rock this. it's very good comparison between the if you have isotropic reservoir rocks and if you have anisotropic reservoir rocks. So in anisotropic reservoir we have a strong stress shadow as compared to isotropic rock. So we can see here we are getting more propagation of this outer and also inner fractures. But in this case, many fractures are terminating and this is getting not that much propagation. And but the simulation parameter was both for both of these simulation. But in isotropic rock, we are getting a small, relatively less stimulated reservoir volume as compared to isotropic. So rock properties, injection parameters, and reservoir stress, all things impact your hydraulic fracture propagations. So so this is how. Let's see another case where, in this case, I simulated some propent and using this DFN. So this like basically here basically we have this big hydraulic fracture, and this have been connected with some of this natural fracture set. This is very simplistic DFN which can exist in oil gas. Maybe in the field this might be more complicated, not that simplified, but this was to test how the propant will behave in this situation. So so in this, let's say here how the propant is working here. Yeah, so let's see how the propant is going. And in this case have very relatively kind of bigger 4070 like 0.3 millimeter diameter propant, and it was simulated with water. So we can see this. So we can see uh, so propant is mainly like concentrated in main hydraulic fracture here, but some part of that propant is going to natural fracture which is directly connected to this hydraulic fracture, and some of this also going to tertiary natural fracture. But overall the stimulation is not that significant because this other part is not probed area, so they become almost like unprobed area. So let's see other other case. Let's see. Yeah, so in this case, what I try to do I increase the fluid viscosity because earlier was the water, so so that water gives a lot of like propellant settling because it has low viscosity, so it has less propellant carrying capacity. And this I increase the fluid viscosity. All other parameters were same, but I increase the fluid viscosity to instead of 1 centipoise, I gave this like 200 centipoise. And now let's see how the propellant will behave in this case. So in this case, we will get relatively more propellant in natural fractures also. It's not completely contained within the main hydraulic fracture. It's also going to other natural fractures because the propellant mass was same, so it's distributed over more natural fractures. So we can see that it's not more red part here. So it's going to also to all these natural fractures also. So so the key point here, if we use high viscosity fluid, probably we can propagate like we can probe more like a reservoir area, but it also has the other kind of other kind of complexity because high viscosity fluid can damage your natural fracture structure and those things. So mostly the water is more like appropriate for the unconventional reservoir stimulations. So this was all about the mainly the hydraulic fractures in oil and gas reservoir. Let's see some of these propagation in geothermal reservoirs. Like I said, geothermal reservoirs, they are not kind of sedimentary. They are not. They don't have this kind of bedding. Is kind of like homogeneous or natural fracture, same kind of reservoir. So here, mostly these fractures, they will go upward growth. If there's nothing to contain them, so they will keep upward growth. And and we don't want, because let's say this is your injection well. So if as we moving upward, so here you have high temperature. As the pressure is going upward, you are is moving towards less relatively low temperature, which is not like desired in the geothermal products. So we want this conductive path mainly here in the higher temperature zone, not in this one. So this is the problem in the geothermal, because they're nothing to contain them, like we have seen in earlier simulation in petroleum reservoirs. So, but one remedy for this one, we found that if we can use let me see, high density fluid, so then probably we can reduce some of because then gravity will act and it will. So this one is showing with relatively less gravity, like 1250 kg per meter cube fluid. So let's see how the fracture will propagate in this condition. So in this one, uh, because relatively low density fluid is still going upward. So in second case, I use like 2000 kg per meter, so it's like almost 2 times of the water density. And let's see how the pressure will behave in this case. So now initially the pressure will propagate almost similar like earlier case, but now since we have high gravity fluid, gravity is like acting downward. So now let's see, we'll see eventually how the pressure will propagate. So with So basically, so what this simulation suggests, if we can use high density fluid, some of this upward growth in geothermal reservoirs, which we have seen in earlier simulation, can be restricted. Now we can compare these two plot very clearly. This is showing this one here is showing very clearly upward growth. It's like giving more upward, and this one is it start showing the downward propagation. But the using having these two like very high density fluid is again then one of the big challenge in the geothermal reservoir, how we will get that thing. So one idea, if we use the high density fluid, so the fluid will make your like high density propant, mix the fluid with the propant, so that will make your fluid of high density, and it can probably like restrict some of these high upward growth. But the problem with that, the propane is very, it's not very much tested in geothermal reservoir, because they have very high temperature, and most of the propane get crashed. What we use in oil and gas, they're not kind of stable. So it's kind of big challenge how we can make this high density fluid injection, and how we can maintain this high density fluid in geothermal reservoir, so that we can restrict some of this upward growth. So other possibility of this upward growth, if you have the natural fractures. So if you have natural fracture, so then hydraulic fracture will probably can hit some of this natural fracture and get restricted. So let's see, in this case we have this naturally fractured reservoir, and then we try to fracture this. This was kind of one new very hot EGS here in Nevada. This case simulation from there, and we have this kind of vertical well, and then we have this production well, and let's see how the fracture will behave in this case. So yeah, we have to wait. It's coming. It's big simulation, so it takes some time. We can see that the fracture is coming up, and it's crosses this set of natural fracture here. So it's crossing this natural fracture, and it's still showing upward growth, because it doesn't hit another so this then it hits one of these the natural fracture, which was almost orthogonal to that hydraulic fracture path, and then it's fully contained. So now this direction has got some free path, so now it just went to these directions. So it's very feasible, because geothermal reservoir, if you have the natural fracture reservoir, then the fractures will be contained. So This study basically shows one kind of comparison of the two DFNs in geothermal, where we have this one DFN where the spacing between this natural fracture set and this natural fracture set was not that much, and when we propagated this process, it was almost like just fully contained, and then it will start basically lateral propagation in this direction. It will open this natural fracture. In this case, we have relatively high, relatively like more spacing between these two setups. Just I think this was like 50 meter, and here I make this like 150 meter, or like this I make 100 meter. And if you have the more like so, spacing between this natural pressure will impact your containment of hydraulic pressure. That's this basically this simulation is showing. If you have high density like spacing, it probably can go upward, but here it was fully contained here. This one. So this is all like comparison thing. Now let's move to some real field case geothermal simulation, which is one of the major project here is going on like through the Department of Energy is like developing one uh, EGS field observatory kind of experimental lab, but it's basically field scale and which is have been developed. Is going on in Utah Force. It's in the very big kind of like $200 million Department of Energy is producing. So it's basically will make a baseline experimental lab from where we can get some like data for other geothermal project development. So this is like force Utah uh, layout of the geothermal like field, and basically rock here is like all the granite, and which have very high temperature ranges from 175 to 225 centigrade. So here they have this main well 16A78. This is the main their injector well. Injection well is like always like went up to 3000 meter, and then after this they already drilled another production well which is like 100 meter approximate 100 meter above this, and it almost like went to parallel to this injector well. And then they have some of these monitoring wells also, microseismic and DIAS monitoring, like I discussed yesterday about. So DIAS we discussed for yesterday for Frac-hit detection, that can also used for hydraulic fracture detection too. So they have all kind of experiment are going on there. So this is like cross section of the reservoir rock, and this is the plant. So they have this one. This is well 6078 injector well, and this is the production well. And then they want to like stimulate this like injector well, and to set a connectivity between injector and production well, so that we can circulate the cold water from this one, and it goes to the rock and get heated, and then we can like extract hot water from production well, and that can be used to generate electricity. So we are at this stage. We already finished this well, and we also did stimulation. Now we are drilling this well, and then we'll check the connectivity. I'm actually at present I very much actively involved this numerical simulation of this field. So let's see how we did some simulation on that. This showing all the reservoir rock. It also have like vertical stress gradient and high Young's modulus rock is dentotite rock. So this is like I told you this last year in April they did three-stage fracturing of this injector well. So there's like some three-stage field scale hydraulic fracturing of that well, and this is very like high natural fracture reservoir. So I took some of this natural fracture close to this. So this was just only one stage I simulated here. I'm still working on another part, but I have this stage three ready. So this is all some of natural fracture are extracted to near to this one, and then we try to fracture this at this point we try to fracture this injector well, and let's see how the fracture will behave in this case. So this is the DFN, so we can see. how the fracture is behaving. So this is kind of very complex interaction between hydraulic and natural fracture. There are like these are like all 32 natural fracture were selected close to that one, and then we are trying to simulate hydraulic fracture in this reservoir. So this once it gets connected with this natural fracture, it gives a lot of complexities, particularly in terms of simulation and managing the like intersection, managing this mess. But somehow we got very good result with also this one. Let's see how the fracture is propagating in this case. So we have to wait for some time again, like earlier case. This is big simulation. So fracture, we can see now it's coming. Yes. So it's again the similar kind of behavior. So in this case, it basically interacted with 4 or 5 natural fractures, and then it's got fully arrested between them, and it should start transferring fluid to this natural fracture, and basically is stimulating the reservoir. So this is the end of this simulation here. So let's see here next. So this was a comparison of this injection pressure what they recorded in the field. So this was like they have variable injection rate was going up. They were like increasing in stages, and then they were decreasing in the final close. So this is where we have is comparison of the injection pressure from the field, which is shown in the red line, and one from the model is shown in the blue. And initially, this up to this we got significant like reasonable match, and at this point, model pressure is reasonable. This is following the physics, because after closure the hydraulic pressure have to close to like your SH mean stress. But in the field they probably got some more natural pressure where the fluid is leaking. So after that their fluid is start decreasing. But that's very hard to simulate. But at least we got very close result here. And this one, they have recorded a microseismic event based on that field stimulation, and then I superimpose that microseismic event on my simulation model, and it's also giving very reasonable agreement with this DFN and DFN simulation, where it have been activated part of the DFN. That part we have getting this microseismic event too. So it's basically giving the good match with that. So in this case, like we have seen propant and earlier in petroleum reservoir. Let's see the how propant behave in this complex reservoir, because once you stimulate this DFN, you want to keep them open for like continuous heat circulation from this like DFN, natural pressure hydraulic pressure combination. So we are interested to pump some propant, but again, because this if you see this, there's not very good connectivity between natural pressure and hydraulic pressure, and so it's very hard to bigger particle the propane is very hard to like pass through these natural fractures because they don't have much opening. So in this we use basically very small size like 400 mesh propant. That's very small size propant. And also consider the reservoir rock, which is like 200 centigrade temperature, which impact the fluid viscosity. So initial fluid viscosity was like 1 centipoise per water, and that due to temperature it was reduced to like almost like 1/10 of that initial viscosity. And let's see how the propellant will behave in this case. So let's see how the propellant. So and here important, this propellant have been simulated after the DFN was stimulated. So once we got this opening, just use that opening in the propellant model, and then we simulated the propellant here. So here we can see some of this propellant is start going to this natural fracture, which are directly connected to hydraulic fracture, but it's still propellant is still remaining mainly in the hydraulic fracture part, like we have seen earlier in, if you remember in earlier the island gas the DFN, there also the propellant was mainly in the main hydraulic fracture. So let's see here. So this slide here is showing a comparison of the reservoir like temperature, how the like fluid reservoir rock temperature is impacting the propellant behavior. And this case we use like relatively bigger propellant like 4070 like propellant, but in this one I don't consider the temperature. And this one is we consider the temperature. So once you use the temperature is fluid viscosity, like earlier I've demonstrated with two cases, one with low viscosity, one with high viscosity. So with low viscosity we can see is still is going the similar pattern like we have seen earlier in oil and gas reservoir. That is why giving more settling in the main fracture in the downward, because the propane fluid doesn't have that much propane carrying capacity due to reduced viscosity. And this one with the without temperature, and this with the temperature. So in this case, we tested the propellant size. If let's say if you use the bigger size propellant, what will happen? And if you use the smaller size propellant, what will happen? So if you the bigger size propellant, because this fracture, natural fracture is this intersection here, they have very small opening, and the bigger side of propellant cannot pass this opening. So really, all the propellant will still remain in hydraulic fracture. But if you use smaller size propan, we can basically probe more area of the DFN. So it's this simulation basically suggests that micropropan or small size propan have more more impact, or we can, if you use the smaller size propellant, we can stimulate more area in geothermal reservoir. So this is what was all talked. So, in summary, I can say that hydraulic fracturing play a very critical role in production enhancements, both in petroleum and geothermal reservoir rocks. And we have seen that in unconventional oil and gas reservoir, due to sedimentary nature of the formation rock, fractures are usually contained and mainly extending in the lateral direction. Whereas in geothermal reservoir, preferred growth is upward, is like upward growth until unless we have some natural fracture and hydraulic fracture interaction that we can contain them. And also this simulation suggests if you can use high density fracturing fluid, we can probably encourage some lateral extension in geothermal reservoir too. So it is finding underscore the significant impact of natural fracture on hydraulic fracture in EGS and also in oil and gas too, because we have seen in this simulation too that so all these need to be higher like more advanced modeling and advanced tool to successfully stimulate geothermal. So this is like one initial study for geothermal geothermal stimulation. So there are a lot of things still need to be solved for geothermal, but it's promising. We can most of these technique which have been used in oil and gas, they can be transferred. They can be transferred and modify enhancement for geothermal stimulation too. So this is my conclusion. So some of the, if someone is interested, some of the publication from all by this particular work can be found here, and so can be found on my Google Scholar too. So this work was supported by DOE Utah Force project, and that's the support is highly appreciated. And part of the project was also supported from this Altarock Newberry EGS project. That support is also highly appreciated. So with this, I say thank you all of you to listening me to this interesting topic, and now I'm open for any question you have. And before that, here in University of Oklahoma in Geomechanics group, we always keep looking the good student. If somebody like interested in geomechanics or have some numerical modeling kind of experience or interest, he can you can reach me, and I can probably talk to in my group if they have some PhD or master position if somebody is interested. And my email is here, so we can reach out anytime to me. Okay, thank you. Yeah. Now I'm open for questions.
If anyone has questions, please unmute.
So we have some doubts in chat box. Can you check your paper?
Yes, sir. Let me take it. Okay. So the first question is from this is Santosh. Hello.
Yes, sir.
Yeah,
Yes, sir.
Santosh. Santosh. You have some question about why fracture is upward growth in geothermal reservoir. Yes.
Yes,
Hello.
sir.
Yeah, so like I explained, mainly depends on this reservoir stresses and also the containment. If you don't have any kind of bedding, just like homogeneous continuous reservoir, so and your formation stresses they decrease with the formation. Like if you go, let's say start from bottom to up. So as you going bottom to up, your stresses are decreasing. So fracture will always try to propagate in the lower stress zone. So so in that case, it will always show upward growth until unless you get some kind of natural fracture or something there to restrict it. Like earlier like further simulation I've shown, if you have natural fracture, it can probably hit some natural fracture and then it can be contained. Okay. Okay. You got your answer. And second
Yes, sir.
question, yes, second question. While hydraulic fracturing, if sand production becomes more than what the actually the Isan, this sand production basically doesn't happen during hydraulic fracturing, I believe. So it basically happened during production. So, but I think we need to figure out some more reason. I never worked directly in the sand production, so how we can control that thing. So that is not basically directly is related with hydraulic fracturing. We can control with that one, but I need to look that question more. Thank you. I will probably get back to you. Do you have some more question? I think these two questions. Do you have another one? Some more?
Any more questions? Please ask if you have any.
Hello, sir.
Yes. Yes.
Actually, I have one question. So, in the
Yes.
natural
Yes.
fracture reservoir, the proppant
Yes.
settles in proppants usually settle in hydraulic fracturing, not in the
Yes.
natural fracture. So, what is the
No.
main
No.
reason?
Main reason is the fracture opening. So if there is not very well connectivity and not much opening of the natural fracture, so propellant cannot pass. And other there is like propellant is function of two things. One is the fracture width, fracture opening, and also the pressure gradient. And since we are simulating this thing with the water, so in that the water doesn't create that much pressure gradient, almost uniform pressure in the whole system. So there is like very less pressure gradient. So and the pressure gradient mainly high in the hydraulic fracture parts. So that's why it cannot enter. But same time, if you remember, I've shown one example when we use very small propellant size. So even that is small opening of this natural fracture, propellant can still go to those natural fracture also. So, but in practice, even like field practice, it's not very much known if you have natural fracture reservoir where the propellant is going. Mainly, it's staying in the hydraulic fracture because that's where it gets more opening and more pressure gradient. Natural fracture is not getting that much propellant. So that's the reason that this micropropane concept came. Before this, when they don't have this natural fracture, the reservoir, they're all like bigger size propane. So in conventional, they're all bigger size propane. In unconventional, when it started particularly looking this natural fracture, hydraulic fracture, so then this concept of micropropane came. There is like 200 mesh, like 400 mesh propane will be almost kind dust. So how it can like like maintain conductivity is very But I did one paper back in 2019 where I did extensive study on micropropant, and we see that they are working good. They give good productivity if you use micropropant. So even also in the geothermal, if we can use that small size propant, we can stimulate natural fractures too. Okay, you got your answer?
Yes, sir. I got it. I
Okay,
got my
okay,
answer.
okay. Some more. Yeah, it's interesting to talk. Let's talk some more questions. Yes.
Hello, sir.
Yes.
Sir, are any geothermal projects going on in India?
Yeah. So one geothermal project, actually, one of this consultant I was talking, he was like one of my friends' father. He was here. So one big project India is trying to do in Ladakh. So I think they already drilled one well up to 500 meters. So and that ONGC is taking care. So government is very interested to do that thing. So it's like it's in development. So I think from next 1 or 2 years they are trying to install the power plant, at least like 20 megawatt power plant. So that the testing is going on there. Yes. And some additional work like kind of research. IIT Bombay, I think under Professor T.N. Singh, he's doing a lot of research and looking potential for geothermal development in India. Yes, thank you.
Hello.
Yes, yes,
Hello,
Isan.
sir.
Yes, sir.
Yeah, I was
Yes, Isan.
asking,
Go ahead. Go ahead.
sir, can we make any some project or some research work on this topics at hydraulic fracturing or something like geomechanics in our college, or you can say for our interest?
Can you please repeat the question?
Hello, sir. I'm audible.
Yes, yes, yes.
Sir, I'm asking, can we make some any project or some any research work on this topic?
Yeah, definitely. We can look some of this research. Yes. Yeah, you can just get in touch with the email and we can look if we can do some kind of some project. Yes. And really,
Okay,
basically,
sir.
we need to get some numerical modeling experience. Yeah.
Okay, sir.
Yes. Yes, sir.
Sir, I'll definitely connect with you on the email, sir.
Yes, sure. Yeah, this is some from Dak Daks Joshi. Somewhere I read there are different type of fracture based upon stresses and formation immediately above and below a particular rock formation we encounter. Can you please elaborate? Yeah, that's great because I already shown one simple example where I use two like upper and lower barrier which have almost like same kind of stresses like 1 megapascal stresses, but if you have different kind of stresses barrier, so different kind of pattern will be depending on how strong whether your stress is less than your pay zone, then you will get more propagation in that zone. If it is stronger that pay zone, then it will start containment. So that, yeah, very good question. It will depends on the reservoir stresses and the pressure will. So the thumb rule here, the pressure always want to propagate in the least resistance area. So wherever it will give the least resistance, and the resistance basically comes with the stresses. So resistance can also come from the material anisotropy, but most of this time stresses dominate. Stresses is kind of first order, material is kind of second order. So the material anisotropy, Lika properties, stresses, they all can impact your hydraulic fracture geometry and propagation and extend in zone above and below your pay zone. Some more question? Hello.
Is there
Hello.
everyone with their questions? Am I audible?
Yes, yes, Tejasvi, you are audible.
Yes. So thank you so much, Dharmendra, sir, for conducting this workshop on geomechanics. Having you here with us for the duration of this workshop was a pleasure. We believe that everyone took away something new from this workshop because it was so fascinating. Thank you for joining us today. Your presence and contributions are greatly appreciated.
Yeah, so thank you, student chapter at PDEU, and particularly to Hars and Tejasvi for giving me opportunity to present some of my research to with you and your students there. And I really appreciate, and I will look forward in the future also. If you have some other workshop, we will probably discuss some more of my work. And thank you again. Thank you for thank you all of you to joining here. Thank you.
Thank you so much for
Yes.
Thank you, everyone. You can leave now.